Okay, next we will have Zenon Saavedra, also from Universidad Nacional de Tucumán. Hopefully I'm getting that one close. On the ray tracing block of a skywave over the horizon radar simulation tool.
Good morning. My name is Zenon. And today I would like to give this presentation about the skywave over the horizon radar simulator, where the performance of this type of the radar depends of the state of the ionosphere. This simulator is developed by the research group of the Telecommunication Laboratory of the National University of the Tucumán, Argentina. Okay, this is my outline of my talk. And I will begin with the motivation of this research, which is the development of the OTH radar simulator. The development of this kind of radar was the basis of my PhD thesis done under the direction of the Dr. Georgina Elias at our university, which was finished in the 2020. And after that, from 2021 to 2023, we worked in a research project for the Defense Ministry of the Argentina. And the topic of this project was the continue with the development of this simulator. That was the reason that this is create of this simulator. Okay, the first question: what is OTH radar? OTH radar is a type of the radar, basically, with the ability to detect targets a very long range, typically 100 to 1,000 kilometers beyond to the horizon. The OTH uses the ionosphere as a reflecting layer to increase its range, the same. With that, the radar can detect the target beyond the horizon. The operating frequency of this radar is from 3 to 30 megahertz. This range is a consequence that the ionosphere can reflect the electromagnetic wave in this range of the frequency. Okay. Okay, here is a schematic diagram which shows the physical process in both in the transmission and the reception, this kind of the radar. For example, in this picture, we can see a model of the noise and model of the radar cross-section, the footprints. In this part are two very important models. They are propagation model and propagation channel model. Okay, these two models are the focus of this presentation. In the propagation model is where is used the ray tracing, and on the other hand, in the propagation channel, we use a model of the ionosphere. This diagram block is a diagram of the simulator, where the second and the third block, they are ray tracing, used by determining the propagation path from the radar to the target, and in the other case, the target to the from the target to the radar. Okay, now I will speak about the ray tracing part of this simulator. It has always been a challenge to establish radio links with the radar system using the ionosphere as a reflector due to the complexity of the electromagnetic wave propagation through the ionospheric plasma. The ray tracing technique is commonly employed to solve this problem, and not only the radar, but other systems using high-frequency electromagnetic wave that travel through the ionosphere. As can be seen in this figure, for example, the satellite communication, broadcasting for here, or obviously this kind of the radar, the OTH radar. Okay, some aspect of the ray tracing. And ray tracing can be used to determine the basic parameter, for example, direction of the energy flow, phase group, and actual paths, integrated absorption, delay of in the propagation, and the other parameters. To obtain this parameter, we have to resolve a group of the integrals, where the key parameter in this case is the refractive index. And this refractive index is belong to the ionosphere in this case. The ray tracing block in our simulator offers three options to resolve this basic ray tracing equation. The first option is 3D ray tracing algorithm based the John Stephenson ray tracing code. The second option is an analytical solution for range. And the last is the more easy, is the Snell law applied to the layered ionosphere. The difference among these three options is the accuracy and the computational runtime. In addition, only for the first option of the ray tracing, we have several options for the electronic density profile. In this case, three options: Chapman layer, parabolic layer, and use the model ERI. The same with the refractive index, three options, and in this case we can choose we want to consider or not with for example, the magnetic field or the collisions. We can choose if want to consider or not these phenomena. Okay, the next slide we will skip because the last talk with Dr. Anelias described of this type of the ray tracing, the ray tracing basically in the Stephenson and Jones. That slide will skip. The next is with the approximation. It's the same that the last talk, and the next is the same. We skip this part, and we stop in this part. In this part, we talk about the input variable and how this affects the ray tracing algorithm. On the other hand, we saw some results. Okay. We can make two type of analysis. The one is considered in having the one consists in having a fixed radar and target. Target is here, and the radar is here. The target is here. And with that, and use a homing procedure to analyze the signal frequency and the elevation angle that connect the radar to the target. In this case, we can see one fourth possible propagation path that be able to connect these 2 points. This is the other analysis consists of the locate the radar and analyze the position of the radar is fixed, We are analyze how the rate path and range vary with the signal frequency and the elevation angle, while keeping other parameters are constant. In this picture, the frequency, the carrier frequency, its value constant equal 10 megahertz, while the elevation range can vary from 10 to the 36 degrees. In this case of the bottom part, the elevation angle is a value constant equal 30 degrees, and the frequency is the parameter variable from the 10 to 11 megahertz. In both cases, we obtain different propagation paths independent of the value of the frequency or the elevation angle. Here is another example with our code where the frequency is variable and the elevation angle is fixed. In this case, the angle is fixed in a value 15, and the frequency, the variation of the frequency, it's between 10 to the 20 megahertz. Okay, here we have the variation of the ground range with the parameter f of f2, parameter of the ionosphere, and the other parameter who is variable is the elevation angle. In this case, the 5 and the 15 grades, and the parameter f of f2 from the 6 to 12 megahertz. And this result only use two options of the three options in the simulator. In the first is the analytical ray tracing, and the second is a Snell law only option. In this case, don't use the third option, that is when we can use the Stephenson and Jones equations. Okay. In this picture, we have a clear, strong variation can be noticed, not between the options, because are very similar, the two options with the both option of the ray tracing, but with the variation with the parameter f of f2, it's very strong. We can see that how the ground range depends of this parameter. And in this part, we observe the variation of the path if we change the value of the magnetic field, the earth of the magnetic field. In this case, the first line is when we consider without a magnetic field, and after that, the rest of the line correspond increasing magnetic field intensity. Yeah. Oilies in this case, we can see that the path propagation depends of the level of the magnetic field in this case. Okay, and finally, let's move. We have the discussion and conclusions of this talk. The first is the ray tracing block is a key part of in this case, the over-the-horizon radar simulator. It's a very important part of this simulator. The other is that analytic ray tracing techniques are much faster than numerical approaches, but they have several restrictions. Yeah, okay. It's because when we can use the ray tracing with for example, when apply the Snell law, we don't consider the magnetic field not consider the collisions. Okay, this is very important. And the ray tracing is very sensitive to the electron density of the ionosphere. And it's, on the other hand, it's sensitive to the model used, the model of the ionosphere we can use. Okay, the future task. The first is implementing the homing in the first and the third ray tracing option. At the moment, only the second option had this option, the homing. The first and third, it's not again. Second, include the ionosphere disturbances. This is very important. Make a sensitive analysis to the inclusion of the collision frequency, which implies a complex refractive index and the possibility of the estimate the loss due to the ionospheric absorption. And the last is the inclusion of the machine learning and artificial intelligence. For example, in this case, introduce a fourth option of the ray tracing, where we can use the machine learning to determine the propagation path and don't use the common model like the Jones and Stephenson or Snell law, for example. And after that, that's all. And thank you very much for your attention.